Hi, I'm Sarah Barrier, and I'm going to be going over the data structure disjoint set, which is also known as union find. This is my final project for UC Berkeley's Data Structures and Algorithms course. So today we're going to go over the motivation for the data structure and a high level of what it is. We'll get into some examples, and then we'll dive into a deeper understanding of the data structure and its implementation. We'll go through things like optimizations, complexity, alternatives, what algorithms use it, as well as having a short code demo. So the motivation. Many software problems contain objects that over time become more and more connected, and it leads to certain questions. Are these two items connected, which can show a cycle? How many groups currently exist? If I connect these two items, which group do they belong to now? Enter the disjoint set data structure. What exactly is a disjoint set? It's a collection of sets that do not overlap. The disjoint set data structure manages groups of connected elements, and its main purpose is to answer questions like, are these two elements in the same set? So some examples. Social networking is the most popular. Network connectivity, power grid nodes, roadway planning, image processing, and scientific simulations that model spreading or clustering. Think about forest fires or disease propagation. Okay, let's get into the implementation a bit. So each set, which you can think of as a tree, a set, a group, each set has a single element that will represent the entire set. And that's the only element that points to itself. In this presentation, we're going to refer to that representative element as the root, and you'll often see it called that in the literature. Sometimes not, but often. So when you initially create it, every element will start out in their own set. And you can see here, each item is pointing to itself. They are all roots. An array is often used to implement this. And the index of the array can represent the item, and the contents at that index can represent what parent it's pointing to. So currently we have everything pointing to itself. So the main functions of disjoint set are union and find, which is why this data structure is often called union find. And they're pretty self-explanatory. Union will take two items and merge their subsets into a larger subset. And find will tell you what subset an item is in. And it'll tell you that by returning the root of that subset, which you'll start to see in the example I'm about to show. So let's see how this looks. So we're going to union 1 and 3. So previously, everything's pointing to itself. And we come in and we say 3 now points to 1. And you can see both visuals of this. Then we union 6 and 7. 7 now points to 6, and you can see the index 7 is showcasing that its parent is 6. And now we're unioning 3 and 7, which you might expect to see 7 here now holding 3. But 7 has the parent 6, and 3 has the parent 1. So 6 is now going to point to 1. Now on to find. Find, if you remember, will tell you what subset an item is in. When you find 0, it's going to return 0. 1 is going to return 1. 3 is going to return 1. And 7 you might think would return 6, but remember, it's returning that root element. So it's going to look and see, am I my own parent? If yes, then you return, but otherwise you go up a level and repeat. So 7 says, am I my own parent? No. Let me go to 6. Am I my own parent? No. Let me go to 1. Am I my own parent? Yes, returns the 1. So the naive approach for the union method would be to just arbitrarily connect the second tree to the first, or vice versa, and to not think about it in a more efficient way. The optimization of that is union by size. So you keep track of the approximate size of each set, and you'll connect the smaller one to the larger. This will keep the tree shallow and will speed up that find operation that's walking up the path. You want it to have one less or fewer steps to take to get to its root node when you're calling find. And this will help in that goal. Now with the find function, the naive approach is basically just doing nothing to mitigate the potential for long paths that can be created with multiple calls to union. So if you're just unioning over and over again, you could get a very imbalanced tree. And then when you try to find what set a particular node is in, you have to go up a very long path to get to that root. So the optimization here is called path compression. So every single time find is called, every node that's on the path from that node to its root is updated to point directly to the root. And over time, the tree becomes flatter and it gives very fast access. So, which leads us to complexity. So this is all based on an implementation that uses the optimizations we just looked at, union by size and path compression. So construction and space both are based on that array that's initially created. So they're O of n. But then union and find, due to the union by size and the path compression, they are amortized and represented by the inverse Ackermann function, which grows very slowly. So in practice, this behaves almost like constant time. Let's get into the code demo. I've got two classes here. One is the non-optimized and one is optimized. So we'll start with non-optimized. And when you initialize this class, you pass in the size and create an array where each item points to itself. In find, you check, am I my parent? If so, you return that element. Otherwise, you recursively walk up the parents till you get to pointing to yourself. And then union, as we talked about, you find the root of each item, and if they're already unioned, you just return. But otherwise, you naively set one to be the parent of the other and return. So let's see this running. So this showcases exactly what we did in the previous slides. We started out where every item points to itself, and then we pointed 3 to 1, we pointed 7 to 6, and then we pointed 7 to 3, which effectively pointed 6 to 1. Then we tried to find 0, which is pointing to itself. We found 1, which is pointing to itself. We found 3, which is pointing to itself. And then finally we found 7, which walked up the path to point to 1. Okay, now let's look at the optimized code. Oh, before we do that, at this point with this naive code, if we were to join 0 and 1, here, let's take a look at a picture to showcase what we've got. So this is what it currently looks like. 7's pointing to 6, which is pointing to 1. 3 is pointing to 1. And everything else is pointing to itself. If we were at this point to join 0 and 1, this naive code would point 1 to 0 as its parent, as its root. And then we'd have a longer path if we called find on 7 to traverse. And let's see that in action. So here we're going to union 0 and 1. And yes, 1 is now pointing to 0, creating that longer path. Now let's take a peek at the more optimized code. So when we initialize here, we're adding in a size array where everything is currently a size of 1. And we're also keeping track of how many sets we have. So the find function has been updated to not be recursive, just for clarity and ease of going through together. So we start out by finding the root, and then we're adding in this optimization that we go through, and for every element, we set it to the root as its parent. So we're constantly compressing the path every time we call find. Then we move on to union, and we've updated that to look at the size, and we connect the smaller tree to the bigger tree. And if we're doing a union, we make the number of counts less because we've merged 2, we now have 1 less group. Okay, and added in an isConnected function as well. So let's see that running. So far, everything looks the same. We've created a function, an array here where everything points to itself. We currently have 8 sets, 8 groups, and we do the same thing. We point 3 to 1, 7 to 6, 3 to 7, which effectively points 6 to 1, and we're back to this point. Now let's see what happens when we try to join. Oh, and as you can see, I'll just showcase, we have 5 sets, 1, 2, 3, 4, 5, which is showcased here. So now let's try to join 0 and 1 right here. I'm going to continue. And you can see that now we have 4 sets, but instead of 1 pointing to 0, 0 now points to 1. But not just that, we can also see that 7, instead of pointing to 6, now points to 1. And we've come to something that looks like this. So this is a much more efficient structure. If we call find on any element, the path to root is short, it's been compressed, and we've joined the smaller item to the smaller set to the bigger set. Okay. So what are some alternatives to disjoint set? Without this data structure, connectivity would have to be recomputed using breadth first search or depth first search, which is much slower, especially when connections are updated frequently. It's not a good alternative. And what algorithms use this? Let's find out. Many do, but the most famous and popular use of disjoint set is Kruskal's minimum spanning tree. Minimum spanning tree, just a reminder, it connects all of the nodes of a graph at a minimal edge cost. So there would be no cycles because that would increase the cost. So it uses disjoint set greatly in the merging of nodes. The algorithm starts by sorting all the edges by weight. So the smallest weight is at the top, and it merges until everything's connected. And it will use union to do those merges, and it will use find to avoid any cycles in the final tree. So that is disjoint set in a nutshell. Here's a reference for the grid of dots picture in the beginning. And I read a lot, I watched a lot of YouTube videos, but of everything, this playlist that I have referenced here was the easiest to understand and the best visuals. So it's a great resource if you want to go learn more about disjoint set. Thank you very much.